You can stop.
That's the only reason.
Right, okay. So, data structures. Are you familiar with the concept of data structures? Anyone? Okay, good. So usually, data structures is about how you store data in a computer. Usually you just store, your data in an array. If you do any programming, you would just sort of define an array A, which is just basically a list of objects, a list of numbers, if you want to make it easier. So let's call them x1, x2, up to some xn. And basically, this is the basic data structure that you work with in programming. So you define basically an empty list. So this is called an array. You can think of it as a vector. Arrays more generally are like matrices or multidimensional matrices. You define an empty array of fixed length n. And this fixed thing is the problem with arrays. It's basically the big drawback of an array is that you define a fixed space. So this is good for some and most things you'll encounter. If you just need a list of numbers or you need a vector, maybe if you're working with vectors, you know how many dimensions you're going to be in, then it's okay to fix the length of the vector. One example that I read of where like arrays are perfect, if you're keeping a high score list, like a game, then okay, you may want to keep the top 10, so you just do like 10 numbers. You're never going to change that. It's a really bad idea if you want to keep like all the scores of a game, because then the array keeps growing and growing, and then you have to redefine it. Maybe not every time, because you can expect that, okay, if I double it, then I don't have to redefine it for a while. But if basically, if you don't know how many elements you're going to put in, then array is a bad idea. Because defining an array takes a lot of time. Basically, what you do is you clear out n spaces in the memory. It's going to be consecutive most of the time, which is like rejuggling the memory, something that takes a lot of time potentially. So you just want to define it once and then keep it like that. So the drawback is the fixed size. But for most basic programming, an array is good enough. Like if you don't do anything heavy, this works with this. Another basic idea is to do a linked list. So this is a more lightweight approach, I guess, or it's more a dynamic approach where you don't know how many elements you're going to have. So for every element xi, you also store, like right next to it, you store a pointer. Let me explain what that means. To element x I plus 1. So an element is a pair of just xi and some sort of, I call it address of I plus 1. So this tells you where in the memory to look for xi plus 1. So this sort of points to next pair, which is going to keep an address to I plus 2. And then in the end, you have like an empty address at the end of its list. So this tells you where in the memory to look for x sub I plus 1. think of the memory as just like one long list of cells. Just like, this is the memory of the computer. Each cell is like 1 byte, like 1 byte of information. And so when you store an element in general, if that element has size that is 10 bytes, then it usually takes up like 10 consecutive spots in the memory. And if you want to point to that, then you just say, okay, this element starts at this point of memory and like ends further ahead. This is not really important, but it's like if you use a list in a programming language, this is usually probably what you want, what you're using. And these are much dynamic. It's much easier to add an element to a list and remove an element from a list. And the size keeps changing, rather than in this case where we have fixed sizes. But these are both very basic and pretty slow if you want to do bigger programming. So linked lists better for dynamic problems where the size keeps changing. Now the big problem with linked lists is that if you're looking for a particular element, it could take a long time to find it. Because basically each time you're looking for an element, you have to start at the beginning and then just look through, keep jumping until you find the element. So, which you can get around with, I'll just say, it can take a long time to find a certain element. And there are ways you can get around this. Like you can always sort of make things faster by using more space. You sort of keep an array of it. Like if you accompany this list with an array that sort of can give you enough information to find things quicker, then you're sacrificing space, which is like there's always a trade-off basically between speed and space. So. Let me just say, hash functions are generally just a better option for storing things than arrays and linked lists. And that's for like big problems where speed matters and storage matters, and dynamic problems where elements keep coming in and out, stuff like that. So I'm going to do a real-world example just to sort of make it more natural, because I don't want to keep talking about memory and stuff like that. I think it's easier to just do sort of a practical example that explains what's going on. So I think my example would be, so imagine you're at a post office or something like, or it could be like a bank vault, somewhere where you want to store things. I think a post office is good because it's very dynamic. Things keep coming in and out. So let's use that example. So suppose we're in a post office that deals with packages. We're looking at the package thing where they keep packages for people to pick up. So let's say they have M storage units, I don't know, pigeonholes, things to put packages in. And packages keep coming in, so coming in and being picked up. So how do we store these so we can find them easily? Basically, just don't spend too much time working on putting them in the right place and then looking for them. This is the kind of problem that hash functions are dealing with. So, how do we store packages? Right. So basically, a simple solution here would be like, okay, when we get a package, we just put it in a box and then we write down where it is. I don't want to do that because that's sort of the storage thing I talked about earlier. If we want to do the computer equivalence, that means, okay, we're making an array of the same size and we're wasting a lot of space doing that. So we want to save space. By not keeping a list of, which units are occupied and like what packages where. In some sense, we need to know where the packages are, but I'll get into that. So one save space by not keeping a large list. I thought about how to make this like a realistic option. I don't know. One option was like if the employers can't read, so they can't keep a list. List or something. I don't know. Just go with it, I guess.
They don't have computers?
Yeah, no, we don't have any computers, sir. The American Post Office. Good social commentary. Let's see. So what do we do here? So an easy option, just like a real world option, would be to just alphabetize it. Let's say M is, how many letters are there? Like 26, something? 25. We can just say, okay, each unit is just the first letter of the last name. So alphabetize, I don't know, somehow partition the language into n, starting strings. I just say, let's say n is let's say n equals 26. Put what last name should I use? Use that. Package in box n. Okay, so this is an easy way to do it, right? And basically, we want to put it somewhere and then give. So Cloud comes in with a package to himself. Whatever. Cloud comes in with a package to himself. It's a storage facility or whatever.
Absolutely.
And I work there. I give you a receipt saying, okay, it's going to be in number n. But I don't want to keep a list of like where it's going to be. So I give you the letter n, and I put it there. Then you come back and say, no, it's going to be in n. I give it back to you. The problem with this, there could be many n's. Are there any more n's here? No. Whatever, doesn't matter. I wasn't gonna do anything with it. So we want an even distribution. Because like everything in computer science, we just assume that m grows to infinity, like it's a very large number. We don't want there to be like thousands of packages in one unit and 0 in another. So yeah, the number of packages is also going to grow with that. So what's the most like natural idea here? Use randomness. Which is why I'm interested in this. So if we just put in packages randomly into a unit, let's say we have m packages to make it easy. So if we randomly place m packages in m units, what happens? So I mean here, every package is put independently of all the other uniformly. Just pick. Whenever I say randomly, I mean uniformly at random. So the problem with this, I mean this is usually the classic like hash function is just do this. And you say these like there's not going to be two large clusters. Like, so the biggest one, let's say one unit will contain roughly log m over log n packages, which isn't too big, but it's not too small either. Like it grows to infinity with m. So if I come in and want to get my package, and if m is large enough, there's going to be like thousands of packages there. So what I want to introduce is a method that bounds this number, makes it slightly more complicated to place it in the beginning. But basically it makes it easy for the customer. The customer never has to wait with this model. Yeah, so in general, the package, the number of, if you're interested, the number of packages in a unit is Poisson distributed. So the probability that there's like k packages in a box decreases exponentially, I guess. But this is like the birthday paradox. Yeah, m always goes to infinity. It converges to some distribution, I guess.
Are the same n?
Yeah, just for simplicity. We can make this. In general, I'm going to talk about m, which is a constant times n. If you want. Yeah, if n is much smaller than m, this is going to be better. Like if n is much smaller than m, we're not going to have any collisions. Like every unit is going to contain at most one with high probability. But the sort of regime we're working in is that n and m are roughly the same. Yeah.
Sorry, I feel like you probably answered this question, but I still don't quite understand. What would be wrong with just going through each of the boxes and putting an item in it? Is it that like an item may disappear from a box and you don't know which one, and then you have to put another item in or something like that?
So the thing is, it's hard in that case. So yeah, this is like where my comparison to computers is kind of bad. But like, basically, if you don't have a list of which boxes are empty, you would have to check all of them.
Right. Okay.
And if there's like, you know, 1 million boxes and 500,000 packages, that's going to take a lot of time.
So I guess the point is like there's some turnover happening. Like,
what does that mean?
Like some of the boxes are empty, but some of them already have items in them or something.
Yeah.
Okay.
Yeah. So this is like, we're thinking like in the middle of a dynamic.
Oh, okay,
process.
right, it's like dynamic. Okay.
Where, yeah, so the interesting
makes
thing
more
is
sense.
we're close to full capacity.
Okay.
Basically, that's the hard case
Sure.
that we're interested in.
Cool, thanks.
And what's something else? Yeah, so the point of this is like it's very quick insertion into the system. We get some collisions, not too bad. And so basically here we have big O of n or m insertion time. Here we have big O1. I'm going to explain if you don't remember these things. Big O1 insertion time. And then the time to find something is expected O1 lookup time. So big O1 just means constant. It's bounded by a constant as m tends to infinity. Let's see, and it's big O, log n with high probability. Yeah.
How is it easy to find something if you stuck it in a random box?
So I remember, yeah. So you come in, I put it in a random box, but I give you a receipt saying where it is. So you show me the receipt, and I just check that box, and I have to look through at most this many packages to find it.
Okay.
Yeah.
So what is the alphabetized option for that insertion? Can you just look at the first one?
Right. Okay.
This is your hash function.
Sorry. Yeah. This was about. Yeah. This is still a hash function. Sorry.
This is for the lookup time or something.
I thought I had arrays here. Or something.
Oh.
I just forgot what I've written here. This is, we don't have a bound on the lookup time. We don't have a bound on how many. So basically the bad thing here is the big of m lookup time. Because it could be that, a positive fraction of all of them land in one box. So is everyone like comfortable with big O notation? Anyone not? Basically less than or equal to a constant times m. So, right, so this is a problem. Could be a problem. This is very common practice in computer science. This is like good enough most of the time. If you have an algorithm that does something like expected constant time and just logarithmic with high probability, that's very good. Because on average, you're just going to spend a constant amount of time on looking for things.
Do you know what happens if we select 2 random boxes and we put the package in the one with fewer packages?
Yeah, that's like the birthday paradox thing, right? Or the balls in buckets with 2 options, right? The rule of 2 thing.
Do we include that?
So what I'm going to talk about Cuckoo hashing is very similar. So what the idea behind Cuckoo hashing is 2 is not going to be enough. So we're going to choose at least 3 options for where we put things. So let's see, each package is associated with D, which is at least 3. So D is a constant here. D is going to be the upper bound on our lookup time, essentially. So each package is associated with this many random numbers. So the point here being, so someone comes with a package, I give them a list of D random numbers. It's a finite list. I can just give them the numbers and then they're good to go. And then I go to place it. So let's call them, do we want to call them something? So I call the package x, and we call these h1 of x up to h of d of x. So this is like d separate hash functions, essentially. And we want to choose one of them that's going to be good. So let's see if I have quick notes on how to spell this. Okay. So we choose one of these randomly, or sorry, first of all, so if any of the boxes, the units, storage units, h1 of x through h d of x, if any of them is empty, oh yeah, sorry. Yeah. I said the lookup time is going to be bounded by d. It's actually going to be like 1. We're going to make sure there's only one element in each box, which of course means we need to have the number of packages less than the number of units, but not much less than that. So let's see. If any of the units is empty, put the package there. So x is the package in that box. That unit. If more than one, we just choose one randomly. Otherwise, we just put it in one of the boxes randomly and remove the previous package from that unit. So. So put it in one of these D positions and remove the previous package. In that position. Right, so now we have a new package to worry about. This package has D numbers associated with it. We gave it that in the beginning. And we just choose one of those randomly, put it in that box. Yeah, first of all, we keep checking if there's an available place for this to be put. Otherwise, we just kick out another package, do the same thing with that, keep going until we find an empty spot. So this is going to make insertion time longer, obviously. But it's going to make lookup time really quick, because when someone comes in saying, okay, I got these D numbers when I put my package here, we just need to check D different boxes, which is constant. Not in expected time, it's just constant. And what we're playing with is the insertion time, which now is not going to be constant anymore. It's not going to be big of 1. The insertion time is instead going to be this. So essentially we're switching these two, the roles of these two, which is good in this post office example that I thought of, but I can't think of any other place where it's good.
So you're also using slightly more memory because you have to store each one x, which x.
Yeah, you're storing D times and numbers, which is, in general, we only really care about, the big O. It's within a constant, but yeah, that doesn't matter.
Within application, it's
Yeah.
twice or 3 times the memory.
Yeah, in applications it does matter. And like I said things before, like, we don't want to define another array of length n. Well, yeah, here we're doing like D arrays of length n. So it's kind of theoretical, of course. But the good thing is constant lookup time. That could be useful if you're hashing is used, I think, to store like data in the cache memory, which is the really quick memory that's like on the CPU of the computer. And then you don't want to be stuck in like looking for the data when you're like doing some fast calculations or something. So in that case, it's good to like get to the data quickly, and you might want to sacrifice some of the speed, some of the speed to put it in there. I don't know too much about the applications. Yeah.
I think I might miss that point. So what do we do with the package that got removed? If
We do the same thing essentially.
we do the same thing. Okay, so that means the previous packages could be removed possibly.
Yeah.
So that means if it's not in AH1 till HD, it could be changed because when the later package can come in, it's possible that we'll readjust the location of the packages.
Right. So these D numbers are always the same. We can write these on the package when we put it in the first time if you want.
Yes.
And then every time we take it out, we just look at these D numbers, choose another of them, and put it there, and so on.
Once you put it there, you remove the package that's originally in that box.
Yeah.
But where those packages go? So those package also has a H1 till HD link to that.
Yeah, every package. So it's important in this process that we use it for every package that we put in.
So once you generate the random numbers, you commit that to the package, or you commit. So my question is that suppose D is equal to 3, and for 4 packages you write down the same random numbers, triple of random numbers, then you can get stuck.
Yeah. So yeah, it's unlikely. So the point here is again that n and m, like the size is going to go to infinity, so stuff like that happens with probability close to 0. Yeah, but it could still happen, and then you could rehash or something. Like if you're, I don't know, if you get stuck, then you can just do it all from the beginning. It doesn't take too much time. It's a bit of an overhead, but because that's what they. So we've been looking at D and D3 recently. Before that, like D equals 2 is the famous case, but then you get stuck in cycles. Almost like with pretty high probability, you get stuck in cycles where you just can't get out. And then you just have to remove all values and just rehash it. Basically find new random functions. Which is going to take some time, not a crazy amount of time. It's still linear, linear in the amount of time spent on that. But this here, we're showing that with high probability you never need to change anything. With high probability it's going to work out. Or we didn't show that, it was shown before. When did I start?
5:50, I think. But that was like o'clock.
Yeah, okay.
So why is it called Cuckoo?
Yeah, so the idea is like apparently the European cuckoo bird does this thing where like it goes into another bird's nest. It just picks a nest to, I guess, sleep in or whatever. And then the person in that nest has to find another nest to be in, and then kicks that guy out. That's the idea. So let me see. Did I explain enough here? Yeah, I think so. So we keep doing this until we find an empty unit to put the package in. Let me do it more mathematical. Just let's finally get to some graph theory, where you can basically forget, if you know graph theory, you can just forget everything I talked about and just look at this picture, which I think is going to explain it. So this. Okay. So let's see. So we define a graph G, which is on 2 sets. It's a bipartite graph. I'll just show you with a picture. All these definitions are easy with a picture, I think. So on 2 sets, L and R, left and right, bipartite graph, where L equals N and R equals M. And we'll make sure that M is at least 1 plus epsilon times N for some positive epsilon. So this is the number of units and the number of packages. So basically, we have this is R, our set of units, and then packages. Each package comes in, chooses D possible locations. So it just randomly picks C3. It's going to be so messy if I draw 3, but so every element of L has D random neighbors. So this is D equals 3. And we're going to do this like dynamically. So we add, doesn't really matter. So once we're done with this, once we've like added all the packages, the graph itself is going to look like a graph where each x in L has D random neighbors in R. D is a fixed number. The sizes of these three is going to go to infinity. So we choose D with or without replacement. It doesn't matter. Could have like that this vertex chooses the same vertex twice, and you can make sure to avoid that. I don't know. It's not a big point, but maybe something that you worry about. So what this algorithm is doing is finding a matching of this graph. And I'll just give you a picture of what a matching is. I think last time I was here, I also talked about matchings. So a matching is a subset of the edges that doesn't touch itself, essentially. Where, let's say, no two edges in M intersect, or yeah, are adjacent. Right, so in this case, let me see, we'll just draw this up. So when I draw squiggly lines, that's the matching. Straight lines is going to be the non-matching. I don't know, it doesn't matter. I don't have to follow that picture. Basically just a subset of the edges such that these intersect in the picture, but there's no vertex where these two matching edges are both ending. Is that clear to everyone? Yeah. Keep going. So what Cuckoo hashing does is it finds a matching. Where each vertex in L is in an edge of the matching. Let's call it M. Okay, so that's what it really does. It gives you, this graph tells you, okay, there are D options. The matching just tells you which one it is in, which unit it's in. And it's going to keep changing, but the edges are going to be the same. The edges correspond to the D random numbers that I gave to the person that handed the package in. Right? Does that make sense? So the way this algorithm works, so let's just for now consider a case where we start with no packages and we just add them one by one. No packages are removed. It's just an easy setting to prove things in. And then all the deletion and like reinsert and stuff like that follows pretty easily. So suppose packages are, let's be grown-up vertices. X1 through xn are inserted in order from an empty graph. We just start with an empty graph. Not really an empty graph. Let's see. Let me explain. Starting with the graph G0, which is just the vertices of R. There are no vertices on the bottom. And I know I draw left, right on top of left. I don't know. It's conventions, I guess. You say left and right, but I prefer to draw them on top of each other. So this is just the empty set below, and no edges at all. So the first vertex is really easy to put in, right? So just x1 just picks d different vertices, picks one of them randomly, and say this is going to be my spot. Next guy comes in, x2, says, okay, I'm going to choose these. And then, this is not a huge point, but it avoids this one because it knows, like, it can check inside the box and see, okay, there's something there. I'll just pick another one randomly. And just keep going. So let's say this here is going to be G2 with matching M2. So we do this in like stages or rounds. This is after 2 rounds. We have a graph G2 and a matching M2. So in general, it's going to be like an inductive proof, I guess. In general, we're starting. We have a graph G sub k minus 1 with matching M k minus 1, and we want to insert xk. Right, and xk chooses d edges and go through the thing again. So now I guess I can state some results. So this, by the way, was introduced by some history. Introduced by, however you pronounce this, in 2004. To Danish computer scientists, the worst kind of computer scientists. And then, so there's two major like directions that research has gone into, which is, does it terminate? Like, oh yeah, what does epsilon have to be for this to terminate? Epsilon and d in relation. So yeah, just to recall. M is 1 plus epsilon times n, or at least that. And d is, the number, whatever it is. Those are the parameters. So we start this algorithm with d and epsilon as parameters, and then, well, I guess m and n are sort of fixed too, but we're going to let them go to infinity. No. I mean, so whenever we talk about, maybe this is important to mention that, like whenever we talk about like results like this, we say that something happens with high probability, basically saying that with high probability means probability just 1 minus little of 1, I guess, if you want, in terms of n. So like tends to 1 as n tends to infinity. So in a way, we're just fixing like large n and m and showing that the probability is bigger than some function of n. That if we had chosen a bigger n, would have been closer to 1. So it's not really like we say that n tend to infinity, but we're always working on a fixed graph pretty much. So I don't know. I never really thought about that, but.
Can you just say it the analysis way? For all epsilon, there's just the thing, the probabilities.
If you really want to.
I know better than say it.
Yeah, sure.
But I never thought about it.
That is what we're saying, yeah. We don't worry too much about it.
Okay.
But yeah, we work a lot with like big O notation and stuff like that, where you sort of bake things like that into just big O. But yeah, sometimes epsilon's running.
Maybe we do that.
Yeah, yeah. Okay, so what's known? So the expected insertion time is big O of log n to the a for some constant a. It's pretty big. And this has been done by a lot of people, but Alan Fries is one of them. And some Greek guys, some German guy looks like. Mostly Greek guys. Maybe German, sorry. I don't want to go through them. And then, so that's like one direction where it's been going. And then for every d at least 3, there exists an epsilon. Maybe that's time. Such that Cuckoo hashing terminates with high probability. Yeah, with high probability if m is at least 1 plus epsilon times n. So there's always going to be, we're always going to be slightly more than n, but like I think if d is 3, epsilon is something like 0.025 or something, this is kind of small. And then it just decreases pretty quickly. And this was also Alan and some Greek guys. Yeah, this one, there's like, I think 3 or 4 papers devoted to like just bringing the expected time down. Yeah.
Can you describe the relation between epsilon and d?
So I think maybe exponential. I don't remember. Chris?
Do you have to pick epsilon bounded away from 0 in terms of n? Or for a fixed
Oh, I
you
see.
pick it little o n?
So you mean you could?
Well, I want m and n, you get very close as n goes to infinity.
Yeah.
But some
I
simulation.
yeah, I think there's like and this is common in like in hashing in general, where there's like a threshold that you need to be above essentially.
Okay, so you can't pick
But
it
it's
below
below.
n.
I guess essentially the problem is just a matching doesn't exist
Okay.
if m and n are equal. So I think it actually has to be
So it has to be
bounded away from
actually
constant.
bounded away.
Yeah.
Okay.
And then I'm going to get to what we think we've proved. So this is the big one. And this was me and Alan. Right now. Which is basically for every epsilon, there exists a d such that the expected insertion time is constant. And since we're free to choose like d as big as we want, we can just say it's at most 2. it's always going to be more than one, because there's always a positive probability that we have to take more than one step. So 2 is the best in terms of integers. And then of course, if you're fine with something bigger, you're going to get d smaller, which I think which is what you really want, I guess. Yeah, and we're not really saying anything about that it's going to be logarithmic with high probability, but it's going to be logarithmic.
So I'm not sure if you understand the difference between expected insertion time and insertion time in high probability.
So basically what I'm saying, insertion time is a random variable. There's a lot of randomness here, so the expected number of steps we need to take is bounded by 2. But there's a positive probability, there's always a certain probability that we keep going for 1 before eventually getting outside. But then, so it's kind of weird to say like, okay, it's less than log n with high probability, because then you need to know what high probability means. But basically, with probability tending to 1, we're never going to take more than log n steps to finish this. And if we do it a bunch of times, the average is going to be less than 2, I guess. Yeah.
Okay, but for some reason, a funny case just came up in my mind. So what if there are D packages, and they somehow choose this, D+1 package, choose the same D location?
I think this is exactly the right question.
That's a question. Okay.
Yeah.
I didn't get it.
That's okay. It's too improbable. Basically, it could happen. Like that's the thing with all like random algorithms and stuff like that, where bad cases could happen. It's very rare, and when we do it, that could be a problem. For me, like theoretically, I always think like, oh, with high probability, that means we're never going to have to worry about it. But in reality, you actually have like finite numbers. There is a possibility that happens. In this case, it's fine because it's easy to just start over and get a new function. Then we sort of had to drop the analogy with the post office, because then your receipts are invalid. But so in this case, it's not really a worry even when it happens.
Do you have a bound of G epsilon?
Let me try to remember what we did. Yeah, it's like 1 over epsilon. So yeah, I'll say it. I'll commit to this. I think it's true. So it's like C over epsilon. But I think C is probably crazy. So I talked for 50 minutes or something. I kind of wanted to mention the proof. I don't know if anyone really cares. But it's surprisingly straightforward. But we do use the old results, which are not straightforward. So there's sort of like cheating in this. I guess just stop here. So any questions?
Has this been implemented?
I talked to one of my programmer friends, and he said he's never heard of it. So.
Can you ask Werner to do that?
Sorry?
Can you ask Werner to do that?
But I'm sure it is, because like it's the good thing about it is like it's really dynamic. It's really easy to just remove something and then put something new in. And before this was known, or before this came, it's like a really complicated algorithm to do that. Yeah, I haven't seen much about it in the literature, or I haven't heard of anyone using it. Great.
Will you be working as a mailman over the summer?
Thinking about it. Any more questions?
So we're saying that it happens with high probability that it's logarithmic type, so the expected time is not representing actually what's happening.
Yeah, so it's essentially, so we're showing actually that like our big contribution is that if L is between 2 and log some constant times log n, then basically this is geometric. So the probability of insertion time being bigger than L is at most some constant to the L. But for it to be truly geometric, we need bigger L's too. But like, so a geometric distribution means, yeah, the probability increases exponentially. And that gives you very easily just the expectation of this is constant, and it's like less than log n with high probability. Like that's the idea, but then we don't know between log n and log n. You would have to use something different than what we used. But yeah, it's basically pretty clear that it behaves geometrically, which is what you would expect. You would basically expect when you put it in first time, let's see, this is the set of like matched vertices in R. And these are like the good option. If you pick one of these, you're done. So you always have like a positive probability, so like at least probability epsilon over 1 plus epsilon of picking these. But then you might miss, and you go to a new guy, and then he sort of, you expect him to have maybe not this many, but still sort of the probability that this guy can get outside roughly the same, and then it looks a lot like a geometric distribution, and it also does in experiments, which is, you know, it's an exponentially decreasing thing. That's exponential. Any more questions? Joe?
So what happens if you try to push the time down to like close to 1 plus epsilon? Like.
Oh yeah, you can make this as close to 1 as you want it. By just making d bigger.
Okay, but what about if you wanted to even closer than 1 plus epsilon, like 1 plus some little of 1, which is 0 now?
Which are 1 plus, yeah, something that tends to 1. I think it does converge to a number.
Like, could you get, say, an increase, a function, a d as a function of n tending to infinity, but really slowly, in order to get an insertion time of at most 1 plus 1 over log n, say?
Probably. Like, usually if, say if we allow like d equals log n, log n usually like looks constant. Like in a random graph, if you change something constant to log n, structurally it's going to look the same, but then you can, yeah, it could probably converge to 1. I don't know, I haven't tried, but I feel like would probably work. Then you don't have constant lookup times. Okay.